Hello, this is Jack Jackson. In this video, we're going to talk about how we can use integration to find the total area between two curves. So we've seen how we can find the area between a curve and the x-axis, and how that actually led us to how we define a definite integral. But what if we replace the x-axis, which is a horizontal line, with some arbitrary curve on the bottom and find the area between two curves? So for example, we want to compute the area bounded by y equals square root of x and y equals x squared. So first of all, I'm going to graph those two things, and the relevant portion we're graphing is right in here. And so this blue curve is y equals x squared, and the green curve is y equals square root of x. And notice they have a couple of points in common. One is 0, 0, and one is 1, 1. And then from there on, they don't really cross again. So the only area that's completely enclosed as a closed region is this area that we have shaded in green, and that's the area we want to find out. So what we can do is we can start by drawing a little vertical strip, and you can see that with this little, I guess it's a little strip right here, kind of yellowish color or different color green strip right here in the middle of our region. Well, how tall is that strip? Well, it's this top y minus the bottom y, where the top y is the square root of x. The bottom y is x squared. So for whatever x is for that point, the top is going to be the square root of that x sub k minus the bottom, that x sub k squared, and that's going to give us the height of that little rectangle. So notice we don't draw our rectangle all the way down to the x-axis this time, but just draw it from curve to curve. And that's going to be the height of that rectangle. The width then is some delta x. But then we want to have it not just this one, but have a whole bunch of those little rectangles going up and down on this little region, little vertical strips. The vertical strips have a horizontal width of delta x. Now when we take a limit of that, when we add those up, we get a Riemann sum. If we take the limit of that, we get a definite integral, and then our thickness becomes like dx, okay, right there, is what happens to the delta x when we take the limit as the n goes to infinity. That delta x goes to 0. We replace that by dx. Replace our function by just that, same function. And we're integrating from 0 to 1. It's important that we know, well, that 0, 1 are our limits of our left and right. Since we're integrating with respect to x, everything in this integral has to be set up in terms of x. And notice really it's just y2 minus y1 is the height of it, but we have to express those in terms of x's, square root of x minus x squared. The thickness is dx, and these are x values going from 0 to 1. And if you notice, that's exactly the furthest to the left and right that we're going here. And so that gives us the actual integral that we're looking for. Of course, this is not a very hard one to do. Think of this as x to the 1/2. So the power goes up 1 to 3/2, multiplied by the reciprocal, which is 2/3. This one becomes x squared, comes up to the x to the 3rd, multiplied by the reciprocal, which is 1/3. It's still got a minus. And then we evaluate from 1 to 0, plug in 1 and 0. Things worked out nicely here. All these with 0 just go to 0, 1 to whatever power is 1. So this becomes just 2/3 minus 1/3 minus 0, which is just 1/3, which is 0.3, repeating, and that is the area that we're looking for right there. So once again, the key, I think, is to kind of sketch the region. You need to identify these places where they cross so that you know what your limits or boundaries are on your integration. And then what we want to do is we want to figure out what this vertical strip is right here and see what its height is. We could have also done this as a horizontal strip, and it would have been integrating from the x value here to the x value here, which would require us to solve these for x. But so this was easier to set up since they were already solved for y. So we can extend this idea to find the area between any two curves. If f and g are integrable functions, functions which have integrals, on the closed interval for a to b, the total area between the two graphs from x equals a to x equals b is the integral from a to b of the absolute value of their difference, f of x minus g of x, absolute value. So if f of x is always the one on top, of course we can drop the absolute value like we did on this problem. But if they change places, or if you're not sure which one's on top, you need the absolute value. Or if they sort of change places from time to time, then you might get an absolute value here. So for example, if let's see if we can maybe draw a picture here. If you get one curve that's going like this, and then another one's going like that, so here's f's on top, g's on the bottom, g's on the top, f's on the bottom. This integral here is going to give you this area plus this area. So it's the total area between the two curves. Okay, just erase that. Okay, so let's so here, let me give you one to try. Okay, you try this one. When I give it to you, write it down, work through it, then come back, press pause, work it out, come back, and then check your answer. So we want the area in the first quadrant bounded by the following curves. Y equals 8 minus x squared, y equals 2 to the x power, and x equals 0. So there should be some region in the first quadrant that's enclosed by those three curves, and those three curves are boundaries of that region, or parts of those curves are boundaries of the region. And then we want to compute the area of that region. So see if you can draw a picture of it, shade in the appropriate area that we're looking for, and then compute that area exactly. See if you can work that out. Come back when you're done. Press pause now. Well, the first thing to do probably is to graph it, and here we have it graphed. And I specifically said the part in the first quadrant. So if we just, there is an area between the two curves, actually from when they cross over here in the second quadrant to where they cross in the first quadrant, and that's a total area, but this one has the x equals 0, the y-axis is a boundary, and we'll talk about just in the first quadrant. So we're talking about what I've got shaded here. So we can see that x equals 0 is the left boundary, and the right boundary is going to go all the way up to where they touch each other here. And so you want to put those two curves equal to each other. 8 minus x squared equals 2 to the x. And normally that kind of an equation that has both exponentials and polynomials in it, that's going to be something that's very difficult to solve in general. But this one has a nice answer, which is just 2. Let's check that out. 2 squared is 4. 8 minus 4 is 4. 2 to the second is also 4. So it goes through the point 2, 4 on both of these graphs. So that's the point of intersection right there. And so now we have a pretty well-defined area. If we were going from here to here, finding where these two cross over here in the second quadrant is pretty much impossible to find the exact value. You'd have to do something like just approximating it and going from there if you had to find, say, for example, this region between the two curves in the second quadrant. But over here in the first, we have a pretty well-defined endpoints of our integral from 0 to 2. Now, when we draw a vertical strip in, it's like it's like this little part of the grid line right here, for example. It's top curve minus bottom curve. In this case, the top curve is the well, on the part that we're integrating, the top curve is the quadratic, and the bottom curve is the exponential. So it's top curve, 8 minus x squared, or in other words, y top minus y bottom. Y top is 8 minus x squared minus y bottom is 2 to the x. And then we multiply that, so that difference gives us a vertical height of our little rectangle. Thickness is delta x. Add those up. Then we take the limit as the number of rectangles goes to infinity. This becomes dx instead of delta x, and this becomes an integral rather than a sum. So this basically comes to be 3 integrals here. So it's 8 times integral dx, which is just 8x. I'll throw the antiderivative. X squared, we take an antiderivative is 1/3 x cubed, and that one has a minus. And the antiderivative of negative 2 to the x is 1 over natural log of 2, negative 1 times that, times 2 to the x. Now we're going to evaluate that whole thing from 0 to 2. So plug in 2, minus, put the whole thing in, but replace the x's by 0. Let me do the easier part first. 2 to the 0 is 1, so this is minus 1 over log 2. This is 0, that's 0. 2 times 8 is 16. Maybe I should write another step in here. Okay. Well, let me just do this. This first part is 16. Let's do it this way. 2 times 8 is 16. This is minus 2 to the third is 8 times 1/3 times negative 1/3. That's negative 8/3. This is 4 minus 4 over log of 2. Minus 0 plus 0 more plus this minus here and this minus makes plus. 2 to the 0 is 1 and this is 1 over log 2. Okay, so 1 over log 2 minus 4 over log 2 is negative 3 over log 2. Zeros are go away. 16 is, let's see, that's 16 times 3 over 3. That's 48 over 3 minus 8 over 3 is 40 over 3. So the exact answer, really I'm going to do this. That last part's our approximation. What I've got in the box there is actually the exact answer. 40/3 minus 3 over the natural log of 2 is the exact value for that area. Approximately, that's about 9. Okay, it's actually an irrational number, but it's close to 9 when it's all said and done. And again, here is the region. Okay, so that means if you broke this up into little boxes that were 1 by 1, which would be 4 of these boxes together, would be a 1 by 1 square, 9 of those would fit in here. Or I guess since it's 4 each, that would be 36 of the little squares should fit inside there. So you could start by counting the whole number of squares. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And then you'd have to kind of estimate the partial squares and add up and see that that is... we should be getting up close to 36, just a teeny bit over 36 there. Okay, in our next video we'll talk about how to estimate derivative or an area of some shape like that where we're just given a graph of it or a picture of it.